Good day to you. This is Galactic bringing you a special presentation on the binary numbers. Now over here we have Johannes Bach. And what does he have to do with binary numbers? Well, not much really that I know of. But the reason he's in here is he looks just like Gottfried Leibniz, doesn't he? Take a look at Johann. They have the same kind of nose. Their wigs are different, but those were a normal thing to have in those days. So that's our friend Gottfried Wilhelm Leibniz, and he's rather famous for having invented one aspect of the calculus, both of which are necessary, as we know now. They had different approaches to the calculus. Now, what we'll be talking about today is, in our new technology back here, you'll see a whiteboard which says binary number system. Now, what does Leibniz have to do with the binary number system is revealed. AI Overview said Gottfried Leibniz developed the modern binary system in 1689. Now, this chain, I actually managed to tie the chain into the tie. This is a double Windsor nut, and if you'd like to learn how to tie this nut, I can direct you to an excellent Italian gentleman who taught me how to do this. What I should have done was look to see where this gold chain was at the time. So Leibniz did not see it primarily the way we would see binary numbers now, which is, as you probably know, the basis of the computer system. The reason he developed modern binary system in 1689 was as a philosophical tool to represent universal truths and the Christian concept of creation through the duality of 1 and 0. Now, all that means is he had a most interesting and rather, I would say, deep view of the numbers 1 and 0. He developed the aspect of binary numbers whereby you could write them using 1s and 0s. But he actually didn't really see it that mathematically, although, as we'll find out, he was a mathematician after all. He invented the calculus, so you might expect that. But he really thought of it as a philosophical tool. He also saw a connection with the ancient I Ching. He was one of the first Europeans, actually, to really talk about the I Ching at all. There was a priest who was in China that Gottfried knew, and he received quite an interesting, I guess you'd call it a parchment, or I believe the Chinese may have invented paper. We could look that up, but not right now, because we want to talk about binary numbers. But the I Ching is a very interesting binary system. It's an 8x8 grid, and both of those numbers are powers of 2, which of course falls right under the definition of binary numbers. Now, what we're going to see today is a final piece of research that I had to finally do, and found out that, by George, it's a good thing I did do my final research, because I have been heard to use the term dyadic fractions, and that is a term that we will take a look at, that I said was synonymous, although I knew that there was something in the back of my mind that said perhaps they're not synonymous. I only read that in one place. I may have misinterpreted it. Now I know that I should not have said that, because they're not exactly the same. But what's even more interesting is the number system that I developed to describe the circularization of the plane, a two-component number system, which circularizes the plane. That's called a parametricization. So it's the parametric construction of the plane, defying Euclid. And remarkably, this has never been tried, although it has been observed in what is called inverse geometry. Nobody saw the relationship between binary numbers and numbers that are inside the circle rather than outside the circle. And if you know what you're doing geometrically, you can use the fact that if the circumference of a circle is given the value of 1, then reciprocal numbers, some of which, that is a subset of the reciprocal numbers, that is 1 over 2 times 2 over 1 is 1. Well, 1,000 over 1 times 1 over 1,000 is also 1. But you'll notice in those reciprocities, or reciprocal equations, formulas, well, I think that is synonymous, these two numbers that are called reciprocal because 1, actually the reciprocal numbers are any number in the numerator over any number in the denominator, provided they're whole, we'll just say positive numbers. If you invert that and multiply them together, they cross-multiply, as we say, which some teachers of math frown on. Because, is that really what you're doing? Well, actually, with matrix mathematics, you can prove that is what you're doing. It sure looks like what you're doing because that's what you do. And it turns out, if you do that, it turns out to be a reducible fraction that reduces to 1 over 1. So if you say that the circle is 1 over 1, then the reciprocal numbers, half of them would be inside the circle because they're less than 1, whereas their counterpart is outside the circle. However, what I just told you is not something that anybody has ever particularly noticed. And I certainly did quite a bit of research to make sure of this, because it was somewhat into the publication of my geometry whereby I was using what I called dyadic fractions, because I had looked it up, but I should look it up again to check that source, because that's not quite the same as binary numbers. And in fact, the number system that's used to parameterize the plane that I use is neither the binary numbers nor the dyadic fractions, which are very closely related, but there is a distinguishing quality between these three number systems, none of which are linear number systems. And this is also called the proportional number system, but even that has never really come into vogue or mathematical view, except in the use of weights and certain forms of measurement, where when you use a binary regression, like 8 pounds, 4 pounds, 2 pounds, and 1 pound, you may have seen this, you can weigh just about anything that's within that range, because you can make a combination between the two that'll get all the linear numbers, which are the numbers we use to count and weigh things, because that's a linear metric, 1, 2, 3, 4. However, if you say the circumference of a circle is 1 proportion 1, making that a two-component number, very similar to complex numbers, then you can also say that if the value is 1, there will be a circle inside that's 1 over 2, to the proportion that there is a circle outside that's 2 over 1. And so by doing that, 1 over 2, 2 over 1, you have two circles that multiply to the surface. Now, what use that could be is what I discovered. That turns out to be rather profound. But what we want today is to just define what is the binary number system, and then the dyadic fractions, just so we know what those are. They're slightly different. And the number system that I use, which is slightly different yet. Now here, as you may see from the title, this is a Wikipedia article on dyadic rational. In mathematics, a dyadic rational, also called a binary rational, is a number that can be expressed as a fraction whose denominator is a power of 2. And then some examples are given. 1 over 2, that is a binary number. 3 over 2, is that a binary number? No, it's not. And 3 over 8, is that a binary number? No, it's not. And so what's the difference between a dyadic rational and a binary number? A binary number is a subset of these dyadic rationals. These are basically what we would just call fractions. And the reason they're called rational fractions is because each of the component numbers, the numerator and the denominator, are whole numbers. But the denominator does have to be a power of 2, which means that that is more numbers than the binary number system allows. The binary number system only allows powers of 2, and 3 over 2 could be called a power of 2, but it's not a whole power of 2. So the binary numbers are whole powers of 2. However, those numbers, as we shall now check. All right, and now we've switched over to the Wikipedia article on the binary number, where it sets us straight, sets me straight. I had to do this research to be sure of my usage of terminology, which is quite important in all aspects of science, but particularly, you might say, in mathematics. So a binary is a number expressed in the base 2 numeral system, or binary numeral system. This is how you write them. That would be in zeros and ones. A binary number may also refer, so there are two definitions of what is a binary number. The way you write it is called a binary number, according to Wikipedia, but then there's another definition, which is the one we want. It may refer to a rational number that has a finite representation in the binary numeral system, which means it's a representable number, and that is a bona fide term. However, if we go on reading, let's keep going, that is the quotient of an integer, which is the numerator, by a power of 2, which is exactly the definition of a dyadic fraction. So what is the difference that I am in need of being sure of so I can express it to you correctly? What indeed is the number system used in my circular parameterization of the plane? In that case, there's one more restriction. In the two-component multiplication formula, where you have two multipliers, where you have the two component numbers of the fraction in numerator-denominator relationship, the reciprocal of that simply reverses the positions of the two component numbers. That, if the numerator, you see, in this case, you have to be more specific, because when you invert the two numbers, you no longer can fulfill the obligation in binary number system writing or representation, or in the dyadic fractions, which turn out to be exactly what a binary number is, so I was right about that. But what I learned that I need to impart to you, as I'm teaching you this circular geometry, which is what I discovered, the surface number does fulfill the requirements of a binary number because it's 1 over 1. 1 proportion 1 means 1 over 1. So you can write it in one of two ways. 1 over 1 is the standard way we're taught in school. But 1 is a power of 2. It's 2 to the 0th power. And that's more than just a convention. That turns out to be provable. But it's an interesting proof, which I leave to you as homework. We don't need to go into it that deeply. But the binary number system is powers of 2. But in my construction of circular space, it's a subset of those binary numbers, because one of the numbers has to be 1. And the reason is that the center number is 1 over 1. So if you change that to 2 over 1, which is the next higher binary number after 1, then 4 is the next higher number, which when written over 1 reduces, as we say, to the numerator, because the denominator is 1. And that's critical in the system. So this is a subset of the binary numbers that is used to parameterize the plane in the following manner, which I will show you with our advanced technology. And here we have it. You see a circle on this whiteboard. Now I'll bet you can't see that, but I want you to imagine it. That is a circle with a value 1 over 1. Now I'm going to draw a circle inside, and it's at an arbitrary distance inside, but you can see it's concentric. But we're not saying that it's to proportion, because that surface value is 1 over 2. So to the proportion that this circumference is 1, the circumference of this is 1/2. That can be computed, of course. Now, if you take the reciprocal of 1/2, you have 2 over 1, and so since 2 is greater than 1, we can draw this circle out here. And believe it or not, that parameterizes the plane with the world's first nonlinear geometry. And that's 15 minutes, actually 16. I don't like these to go too long because these are supposed to be brief. And this was also supposed to be a podcast where I interview people. Now, I can't actually invite people here, especially when they're 300 years dead, but I was going to interview our hero, Leibniz, about whom we're going to have a few words that don't have too much to do with the binary number system, except they connect Leibniz with his study of the I Ching, which I consider to be a holy book. So that won't be a sermon, don't worry, when I say holy book. But perhaps you should, because I do think it's a holy book. My goodness, what are you in for? Don't worry. But that won't be mathematics. This is. So what we really want to know, is there any proof that this actually, first of all, is coherent, closed, logical, consistent? Does this really do? Why does nobody use this? Because obviously it parameterizes the plane with circles. Well, because it's not linear. And that's what we'll talk about as we interview one of my teachers who died of the COVID virus in 2020, John Horton Conway, who actually helped me discover this number system because it appears in his extraordinary, somewhat miraculous, binary number tree generator called the surreal number system, which is now admitted by mathematicians, finally defines what is a linear number. I was able to corroborate that, and actually, so far I'm the only person who's noticed that. Explicitly, that can be proved, but we'll get into that in the next video. That's 18 minutes. Thank you so much for your patience through this, but I'm showing you a brand new number system that will teach us the collapse of the wave function and quantum gravity. Thank you for tuning in. Keep looking up. We have a new crescent moon. I saw it for the first time this night. It's 4 days, 3 to 4 days into its cycle, and the new moon, the crescent moon in the western sky, is so beautiful that it's heartbreaking. And if you haven't seen Koyaanisqatsi, I recommend the first 4 minutes of that movie. You can watch it for free on YouTube. So thank you very much, and we'll be back with a binary number system whose subset I discovered parameterizes the plane with a new number system that makes a non-Euclidean geometry, that describes space-time, and much, much more. I think you'll be fascinated. Thank you. We'll be right back.